Welcome. So today we're going to tackle something that, let's be honest, can look pretty intimidating at first, multiplying polynomials. But I promise you, it's really just a puzzle. And by the end of this, you'll see there's one simple key that unlocks the whole thing. All right, let's crack this thing open. Okay, let's just jump right in with a picture. Imagine a simple rectangle. Now, what if its sides aren't just plain old numbers? What if the lengths are expressions, like x plus 3 and x minus 2? How in the world do you find the area then? Well, this is exactly where multiplying polynomials comes into play. So you see, it's not just some abstract math concept. It's how we solve real, visual problems just like this one. Now, you might be thinking, great, here come a bunch of new, complicated rules I have to memorize. But here's the good news. You don't. Our entire journey today, everything we're about to do, is built on one single powerful idea. You master this one thing, and I'm telling you, you've mastered the whole topic. And here it is, the one and only, the distributive property. This is it. This is the master key. Our source material puts it perfectly. When you want to multiply a polynomial by a single term, that's a monomial, you just use this property. Think of it like this. The term on the outside gets shared with every single term on the inside. That's it. Let's see this thing in action with a super simple case. We've got 3 times the quantity x plus 4. Okay, step 1. We distribute the 3 over to the x. That gives us 3x. Easy. Step 2. We take that same 3 and distribute it to the 4. That gives us 12. And for the final step, you just put them together. And there's our answer, 3x plus 12. Simple, right? That's the core move. Okay, so you've got the basic move down. Now, what happens when the problems get a little bigger? What if we're multiplying 2 polynomials together, not just one term? Well, the secret is we don't need any new rules. We just use that same exact move just a couple more times. And this is where our source material just lays it out so clearly. To multiply any 2 polynomials, you just multiply each term in the second polynomial by each term in the first one. It's the distributive property just scaled up. Every single piece from the first group gets its turn with every single piece from the second group. This comparison is just perfect for showing what's going on. Look at the left. With the monomial, you distribute just one thing, the 3. Now look at the right. With the polynomial, you distribute each piece from that first group. First, you take the x and distribute it across, x plus 4. Then you take the 2 and do the exact same thing. It's the same move, just done twice. So let's walk through it. First up, the x gets distributed, giving us x squared plus 4x. Then the 2 gets its turn, giving us 2x plus 8. Now we just gather up everything we've made into one big line. But hold on, we're not done yet. This last step is absolutely crucial. You have to clean it up. We have a 4x and a 2x in the middle. Those are like terms, so we can combine them into 6x. And that gives us our final beautiful answer, x squared plus 6x plus 8. So now you've got the fundamental tool to multiply any polynomials you come across. But, sometimes in math, there are these really elegant shortcuts for common problems. Let's look at a pretty cool power-up for a very specific situation. I want you to just imagine for a second you had to solve something like a plus b to the 4th power. Yikes, that means you'd have to multiply a plus b by itself, and then do it again, and then do it again. You could do it with the method we just learned, but man, that would take a while, and there are so many places you could make a tiny mistake. So the big question is there a faster way? And the answer is a huge yes. The source material points us toward one of the most famous and honestly beautiful patterns in all of mathematics, Pascal's triangle. This thing isn't just a cool design, it's a secret calculator, and it's built for exactly this kind of problem. So how does this magical triangle work? Let's just build it ourselves, right now. It's so easy. It starts with a single 1 at the top. We'll call that row 0. Then, the next row, row 1, is just 2 1s. That's our foundation. And here's the one simple rule you need to know. To get any new number, you just add the 2 numbers directly above it. So for row 2, we look up and see a 1 and a 1. Add them together, you get 2. And the rows always start and end with a 1. That's it. And this pattern just keeps on going as far down as you want. For row 3, you add the 1 and 2 above it to get 3. Then you add the 2 and 1 to get another 3. The elegance is in its simplicity. You can just keep building it forever with that one little rule. Okay, so here's a more fleshed out version. But so what? Why do we care about these numbers? Well, here's the connection. These numbers are the coefficients, the numbers that go in front of the variables when you expand a binomial. And notice how the row number matches the power. Row 2 is for squaring something, row 3 is for cubing it, and so on. Which brings us right back to that monster problem from before. For a plus b to the fourth power, we just look at, you guessed it, row 4 of the triangle. The numbers are 1, 4, 6, 4, 1. Those are your coefficients, right there. No long multiplication needed. It's just an incredible, incredible shortcut hidden inside this simple pattern. All right, we've gone from the core method all the way to a pretty amazing power-up. Let's just zoom out for a second and lock in the most important things to take away from all this. So, if you only remember a few things, make it these. First, everything, and I mean everything, boils down to the distributive property. That is your master key. Second, your mission is to multiply every term by every other term. Make sure nobody gets left out. Third, and don't ever forget this, always simplify at the end by combining your like terms. And finally, if you see a binomial raised to a power, you've got a secret weapon, Pascal's triangle. We've really only just scratched the surface of this thing. Pascal's triangle is wild. It has deep connections to probability, to something called combinatorics, to number theory. It's all over the place. Which leaves us with a final thought. What other mathematical secrets do you think are hiding in plain sight, just waiting inside this simple pattern of numbers?